Hello everyone and welcome back to the lecture today. So this lecture is the last in the negative feedback series and today we will cover the Nyquist stability criterion. So in previous lecture we saw that basically there are possibility that in some system at the right frequency it may become unstable. However, we haven't developed uh, a mathematical way to easily determine if the system is stable or not. So Nyquist stability criterion is one of the method that you can easily implement and understand the degree of stability of your system. Okay, so this method will be used to determine whether the system is stable or not. So I believe back into the late 19 no the late 1890s or the early 10 or 20. I'm not so sure. There's a gentleman. His name is Harry Nyquist. He's an American Swedish. Um, him and his college in at AT&T was trying to determine what is the easy way to figure out if their telephone system is stable or not. So he invented a method that help you today to see whether your system is stable and the degree of that stability. So this method today we will go through the process of first we need to plot a diagram that called Nyquist diagram. It's nothing fancy. It's basically a polar plot of the loop gain. Okay, loop gain is once again beta multiplied by the open loop gain or a. So if a or the open loop gain is a frequency dependent function, then loop gain is also a frequency dependent function. Also, because it's a complex function, you have j here, you will have a real and imaginary component. So the polar plot is the plot that you have real on the x, imaginary on the plot on the y. And when you plot, you want to plot in terms of magnitude and phase from when frequency is back to negative infinity to on the way. That frequency can vary from negative infinity to positive infinity. Oops. Second step is to determine if your Nyquist diagram in circle or going through the negative 1 0 point. If it does, then the system is unstable. Mathematically, you can evaluate by considering the magnitude of uh, the loop gain for the frequency omega or f, your choice, the frequency at which the phase equal to negative and 180 degree, so that you can determine the stability. If the magnitude of loop gain is larger than 1, system is unstable. If it's less than 1, it's stable. So let's go through one example for Nyquist diagram for the two-pole amplifier. So we have went through in last lecture we went through a two-pole or two-stage current amplifier, right? So we will use the exact same example. With that example, you know that you can have a loop gain function like this. With if I have t is loop gain equal to beta a, then I just have to multiply beta for the open loop open loop uh, open loop gain function. So I can replace j with omega easily like this. Okay, and in here, just a reminder, the first omega 1 is the upper 3 dB radian frequency from from not from the first stage, and the second omega 2 is the upper 3 dB radian frequency from the second stage. So if I have this complex transfer function, I can write it down in terms of magnitude and phase. Okay, you guys can go back to previous lecture to see, but basically this is the simplified form of magnitude and phase. So if I plot out magnitude and phase in a polar plot, I can have this, and let's go through this together. So what you want to do is basically if you start plotting from um, negative infinity for omega, we will start from here. So when you plot from negative infinity to 0, the plot will go from here to here. When you plot from 0 to positive infinity, it will go from here to here. Okay, so at omega equals 0, what can you see? So since this is a polar plot, you want to consider the magnitude, which is the length of the vector. In other words, if I grab a point right here, and if I determine the distance between this point and the origin, that will be the magnitude. How about the phase? The phase is basically the angle from the original x onto the point that you want to plot. Okay, so for example, in this vector in here, you can see that if I examine this point, I can have, this is my phase, and this is my magnitude. So if I examine this point where omega equals 0, what will happen? So when omega equals 0, okay, I can plug omega equals 0 in here, omega equals 0 in here, this term cancel out, this term cancel out, okay, and this one will become square root of 1 equal 1 multiplied by square root of 1 equal 1, so this whole bottom become 1. So when omega equals 0, the magnitude of loop gain will be equal to beta ai naught. Okay. But also, how about the phase? So when, one second. So okay. So the magnitude become beta ai naught. The phase, how about the phase? You technically have a vector coming from here to here. So this vector have the same direction with the unit vector of the x-axis, right? Therefore, you have a phase value of 0 degree. So that's why I have the 0 in here. Okay, if I examine from 0, let's say to negative 90 degree, then from negative 90 degree on the way, okay, to, I mean, if I examine omega, so I'm so sorry. If I examine omega to like basically an increasing order to positive infinity, so first it will cross negative 90 degree, then it go toward negative 180 degree, right? So as you see, as omega increase, now the distance between your examining point and the origin will slowly reduce and reduce and reduce up to here, just getting smaller and smaller and smaller down to 0. How about your phase? Phase is always negative as you are going, uh, yeah, phase is always negative. Okay. How about if you go from this direction to this direction? That means when you try to examine your from 0 to negative infinity. So for a frequency that is less than 0, or if you try to examine when omega goes from 0 to negative infinity, you can see that uh, the same way the magnitude of loop gain decrease, but now the phase actually is positive, and you can see now you have kind of like a heart shape, right? What what is okay? What is unique about a heart shape is symmetry, correct? So because of symmetry, you can actually have a mirror line in here, and the real axis now can become a mirror line. So you can see that this dotted line here is an exact mirror image of this solid line. This solid line is the loop gain when omega is larger than 0, which is the real case. You always have a positive. You always have a positive. What's that called? You always have a positive frequency, right? It's difficult to implement. It's difficult to really implement a negative frequency. So since you have a mirror line, now the positive, the loop gain when frequency is positive is actually a complex conjugate of the loop gain when the frequency is negative. So what is complex conjugate? So easy way is complex conjugate have the same real but the opposite imaginary. So now let's examine at this point uh, when omega goes to positive infinity. When omega goes to positive infinity, you can see that value of the value of loop gain, the magnitude of loop gain will goes to 0 when the phase is going to negative and 80 degree. Therefore, you can see that when this phase go to negative and 80 degree, this magnitude of loop gain goes to 0. Therefore, this system is stable. Okay, there's no situation that the system become unstable. Okay, so we're safe. All right, how about if you have two pole? I mean three pole. I'm sorry. We have three pole. So we're gonna go use the example of last week. I mean last lecture also with three pole or three stage amplifier. So if we know that the loop gain transfer function, complex transfer function is this, you can write it down in terms of magnitude and phase, right? So here is the magnitude and here is the phase. So we have two cases here. The first case is when the system is stable, and I can draw out my Nyquist diagram. So I can start from from positive 0 to on the way to positive infinity. So what happened is first I get to like the magnitude will start decreasing. I mean, as you remember, okay, it starts stable, it crossed a corner frequency, it start decreasing, uh, until 90 degree. Okay, so at 90 degree, after that it start decreasing more to negative 180 degree. Then it will it will come on the way to negative and 270 degree in here. So if you do the other way, varying omega from 0 negative to negative infinity, you go in this direction on the way down and up. But I want you to examine this point, the point minus 0. So if you draw a vector from here to this point, okay, so if you try and consider the frequency, um, so at the frequency, I don't know what frequency it is yet, but I know that if I prop a point right here, I can find a frequency that make the phase become negative 80 degree, right? So this point is negative 80 degree. If I prop this point and I draw a vector I know that this length of vector will never be larger than 1 because, you know, the vector from here to here, it can never reach this point. This is the unit circle in here. So I know that this vector is always less than 1 in terms of magnitude. Therefore, I know that the system is stable. Okay, so now I will give you a spell Acadabra. If you draw the Nyquist plot or the Nyquist diagram, and the Nyquist diagram does not encircle the negative 0, 1 point, the system is stable. So let's go to case number 2 when system is unstable. So I'm drawing the same thing again, but the main difference is now in this case, you can see that my Nyquist diagram actually encircle this negative 1, 0 point. So if I draw a vector from here to here, so what will happen? I can see that this vector where the phase is equal to negative 180 degree, this vector will have a magnitude of more than 1. So the system will become unstable. Correct? So now I will give you another spell saying if the Nyquist diagram encircle or goes through the negative 0, 1 point, the system is unstable. Okay, so let's go through one example together. So I will ask you to be able to determine the stability of an amplifier for two different transfer function, feedback transfer function. So the first amplifier will have a feedback transfer function of 0.2, and the second amplifier will have a feedback transfer function of 0.02. Okay, and I will give you the loop gain for both systems to be so in terms of frequency f, so I have TJF equal to beta, which is the feedback transfer function, multiplied by 100, which is the mid-band or the low frequency open loop gain or the mid-band gain. Then if you see in here, how many poles do we have? If you answer one pole, you are actually wrong. Okay, the system have 3 poles, but 3 poles just happen to be at the same place, which is 10 to the 5th. I mean hertz. Okay, so if I write this this complex transfer function in terms of magnitude and phase, I can have magnitude will be beta multiplied by 100, then square root of 1 plus f over 10 to the 5th square, then you cube this. Okay, so in other words, because these 3 you have 3 of the same pole, you just repeat this term 3 times. How about the phase? It's negative 3 multiplied by inverse tangent of f over 10 to the 5th. Likewise, you just take this, repeat it 3 times. That's why you take the factor 3 out. So we need to find a frequency, and I will call that f subscript 180. This frequency is the frequency at which the phase become negative 80 degree. Okay, so if I grab this phase term, then I make it equal to negative 80 degree. Okay, can you guys help me find out what is f subscript 180 is? So you divide both terms by negative 3, you have 60 degree here. you know that tangent of 60 degree is actually square root of 3, so you know that inner sub 1 f subscript 180 over 10 to the 5th will be square root of 3. Then you can find that f subscript 180, or our frequency of interest in here, is equal to square root of 3 multiplied by 10 to the 5th. So instead of using the number square root of 3, square root of 3 is around 1.73. So I just round it up to 100. You can use 1.73 multiplied by 10 to the 5th, or you can use 173 kilohertz. Anyway, so the question asks for to determine the stability of two different systems. The first system will have beta equals 0.2. So we start with that first. So we plug in this number for beta equals 0.2. When the when the frequency equal to 173 kilohertz. So you see this phase term in here, you plug in beta equals 0.2, you plug in the phase equal 1.73 multiplied by 10 to the 5th. Okay, so after you plug in off number, you will have a result of 2.5. Now you are the judge to see if the system is stable or not. But I will go through the math for the second system. Beta will equal to 0.02. So I plug in off the number, same, except for now beta I have it to be 0.02. And I have the magnitude to be 0.25. Okay, now you compare this and this, and you tell me which one is stable, which one is not stable. For the case of beta equals 0.2, the magnitude is 2.5, which is a lot larger than 1, right? And of course, the system is unstable. Meanwhile, when beta is equal to 0.02, the magnitude is less than 1, so the system is stable. Okay, everyone, we have finished the negative feedback amplifier. So next we will probably move to chapter 15 and conclude our semester. We will probably try to go through the oscillator. Okay, so I hope you guys learned something new today, and I'll see you guys next time. Goodbye.